Gait and motion disorders are prevalent in older adults. Gait data is complex and multivariate in nature. However, existing tools often focus on only a subset of categories of data. The lack of open access and proper standardization in systems hinders collaboration between research labs and clinics. Existing tools often fail to provide support for crucial features such as comparing patient groups, tracking disease progression, and analyzing anomalies and statistical measures of gait. Identifying these gaps, our goal was to gather comprehensive data processing and data analysis and visualization requirements from Gait practitioners. We plan to develop an open access system that covers the entire workflow of the practitioners. We also plan to explore visual encodings and interaction methods to support tasks such as comparing between patient groups, analyzing disease progression of a patient, and analyze anomalies and statistical measures of the gait data. Conducting a survey and working closely with Gait experts, we identified the holistic requirements and proposed our novel visual analytics system, VIGMA. Users first start by importing our Python library in a computational notebook as shown on the left side. User then has to specify the trial that they want to work with. Afterward, they can perform different functionalities with this trial, performing format conversion, feature extraction, and so on. I'm going to show a simple example of converting formats. Here, as you can see on the file directory, the data is available on a mat format, but we can simply call this mat to CSV Python API, and this will convert it to a easy to access CSV format. Afterwards, user can have access to these different parameters of Gait using this CSV format. User can also use this different functionalities such as feature extraction, missing value imputation, filtering noise, marking step times, saving and loading data to the visual analytics systems, and so on. The entire library is documented in our GitHub repository, and there are examples provided in notebook format so that users can use this in their own system using this easy to use examples for all the different functionalities. After the data processing steps are completed on the computational notebooks, user can then store the processed data and upload the processed data to our visual analytics system as shown on the right side. In the visual analytics system, users first have to set the location where the processed data are stored. After setting the file location, user then do dual or single group exploration. Here we're going to do dual group exploration. First, in the data hierarchical data structure, we're going to access 2 stroke patients. And for group 2, we are going to also select 2 stroke patients, but different ones, and then label them as S1 and S2. We can then visualize different parameters such as joint angles, ground reaction forces, spatiotemporal parameters, electromyography data, and so on. Here I'm going to select shank angles for left side limb and left side cycle for both group 1 and group 2, and opt for visualizing all the trials at once. We can also select to visualize with confidence interval, and we're going to do for ground reaction force for panel 2. And similarly, we're going to fill the other 2 panels with different parameter configurations. User can also select to visualize spatiotemporal parameters with spatiotemporal distribution and summary view, and they can select the spatiotemporal parameters using this checkboxes, and as you can see, the spatiotemporal parameters are visualized on the bottom. All the visualizations are bidirectionally interactive, meaning when we highlight a trial in one of the plots, it is going to be highlighted in all the other charts as well, as you can see. And the highlighting is bidirectional, meaning when I'm going to highlight by brushing the box plots, it's going to bidirectionally highlight different trials in all the other plots. User can also get access to the videos by simply using this checkbox, and it will show the actual raw videos of the highlighted trials. And if we remove a highlight, it will also remove the videos from the video panel. And user can also select different playback speeds on the videos, and when they play the video, the corresponding time series ensembles view, there will be a circular encoding that moves on the time series ensemble views. We can also see that the visualizations are interactive, meaning that when we highlight over a trial, it shows the actual patient ID and trial number. When we move over the spatiotemporal, when we move over the time series ensemble views with confidence interval, it shows the spread values. And we can also remove all the highlights by simply using this reset filter button. VIGMA is validated through usage scenarios performed with experts specializing in gait and mobility rehabilitation. The first usage scenario involves finding anomalies in gait data and fixing it through the system. Visualizing data using VIGMA, we found an instance of negative step length of the left foot for one of the trials from the stroke patients. As we know, step length cannot be negative, and identified this erroneous patient and trial ID by brushing the box plot. Next, we analyzed the vertical force for this trial, identifying a half landing at the beginning of the trial, and validated our speculation by tracing it from the video exploration view of VIGMA. To fix this issue, we used our Python API from a notebook to mark step times by discarding the half landing and loaded the corrected data to the visual analytics system. Afterwards, we could extract the correct step length of the patient's trial. There are 2 more usage scenarios performed with experts and reported in the manuscript. Our system received very positive feedback from the practitioners across different labs and clinics.